last time we looked at propositional logic, and in particular semantics of propositional logic in terms of truth tables. So now we're going to look at how you actually prove theorems in propositional logic. So there we are. Now, what the hell is this? Okay. We have got three axiom schemes, they're called. So what does that mean? Well, the first one is called K. K is simply its name. And it's everything that looks like this. So remember, variables like A and B are like metavariables ranging over any propositional formulas. So this first one says anything that has some formula A implies, then in brackets, some maybe different formula B, and then followed by, of course, the exact same formula A. Every possible thing that looks like that is an instance of axiom K. So they call it a scheme because it's like a system, like a whole family of axioms. I guess computer scientists would call that a macro. Okay. Then the same, there's an axiom S. You'll see there are three different, possibly different formulas making up axiom S. And again, you can plug them in for any A, B, and C that you want and generate instances of axiom S. And finally, DN, which actually stands for double negation, so that's something that makes a little sense. And also, I think the logic here should make a little sense to you because it simply says not A implies A, and you're probably breathing, thank God, as one of them that makes sense. So there we are. We have these three axiom schemes, and an inference rule here, modus ponens rule, I guess that's Latin for means of proof or something. And this is pretty obvious. It says if I have anything of the form A implies B, and I have A, and of course when I mean I have, I mean if the thing is a theorem. So if I have proved A implies B, and if I have proved A, then through this rule I have a proof of B. So this is a real proof system. This is not somebody who got drunk some night and said, how am I going to troll the entire planet? Oh, and by the way, what about things like and or and implies? I'm afraid they're not there. So if you like them, what you've got to do is expand them out, because if you have implies and not, you can express things like and, although they look kind of ugly. And so you can get the effect of all those other connectives simply through abbreviations. So right, there's our proof system. So it's time to prove something, and we are going to prove, all my stuff is going to blow away. We are going to prove A implies A. Now, you probably think that's easy to prove, and I should just get my pen out and prove it in front of you to show how smart I am. But I'm actually not stupid enough to try that, because the way you prove A implies A, and by the way, I think this is like the only way, is with a proof on this slide. Now, there probably are other ways, but this is probably the shortest way of proving A implies A. First, oh, and by the way, sorry to overcomplicate things, but this is in fact a schematic proof in the sense that A is itself, if you like, a metavariable standing for any particular formula that you want to prove this for. So this proves, if you like, all instances of A implies A, regardless of what A is. Anyhow, we generate this particular instance of axiom S. And if you stare at it long enough, you will convince yourself, I hope, that this is indeed what you get. I think all you are doing is plugging in D implies A where you had B before, and plugging in A where you had C before, something like that. And this is a valid instance of the axiom scheme S, and that is our first step. The second step, you look at axiom K and you note that one of its instances includes this thing over here, and then you say, aha, modus ponens, that is, this thing here matches that thing up there, allowing me to deduce that this thing here is a theorem. Oh, happy day. Now, if you're super awake, you might see where we're heading, because this thing is also an instance of axiom K, from which, by a further modus ponens, we arrive at A implies A. Now, I recall a despairing student once saying, like, why can't you just say, like, A is true, therefore A? And the answer to that question is exactly the same as if you are playing football and the ball rolls in front of you. Why can't you just pick it up and run with it? And the answer is, it's not allowed by the rules, right? The rules of this particular system are right here. That's what you're allowed to do, and you're not allowed to do anything else. So yes, proofs even of simple things here grow exponentially. Now, as I said, this particular system is not something crazy, and if you will allow me to give you another aside, this actually connects to type theory, lambda calculus, combinators, and all sorts of things, some of which we still teach you, and some of which we used to teach you when in the remote past I taught a course called Foundations of Functional Programming, and you can still find the notes on my website if you're mad enough to do that, where they are things called combinators which can be used to express things in the lambda calculus without using any variables. And in fact, one of the combinators is called K, and if you were to give it types in a suitable type system, the type of K would look like that. The other combinator is called S, and again, if you gave it a type in a suitable type system, the type of S would look like that. Again, all this is not examinable, but I hope interesting. You can express the identity in the combinatory logic by writing SKK gives you the identity. Now, what is SKK? It is exactly this S, this K, and this K gives us the identity, and the type of the identity is, of course, maps A to A. So, in fact, this crazy system for propositional logic actually has a reason to exist. I should say, there's a little remark here, you will find in various logic texts many other systems for propositional logic where I think somebody did more or less get drunk and say, okay, we need to write some rules, oh, that'll do, yeah, or does the right thing, yeah, it's finished. And the trouble with those, I mean, this one I showed you, this is already essentially impossible to use, but at least it's interesting. A lot of the others are just impossible to use, and they're not even interesting in any way. Now, the last point I wanted to make while in my aside, so my non-examinable aside, is to mention that, and you had the semantics course last term, and I think you had a type system for some kind of lambda calculus-like language, I think, last term, and you had a function application rule that looked a bit like this. And again, what are the types doing? A arrow B, and A gives you B. So again, we have this link between modus ponens in logic and function application in the lambda calculus of type theory, which is, again, this will connect you to things like the types course in part 2 and lots of other things if your mind works that way. Right, end of aside. So back to examinable stuff. So again, though, talking about, well, in particular, we're talking about the proof calculus I just showed you, but the things I'm showing here make sense for any proof calculus that anybody can dream up after drinking too much whiskey. It was Burns night last night. So if I have a proof system, which the provability in the proof system is denoted by this symbol here called the turnstile. So, okay, for the thing I showed you on the first slide, I showed you the axioms, I showed you the rules, and anything you can prove starting with some formulas and using those axioms and rules, we say that A can be proved from S. So either for the calculus I showed you or for any particular one you're interested in, we write S turnstile A to mean that starting with some set of formulas S, we are able to prove in our calculus A as a theorem. Now, if you're coming along and saying, I've got a proof calculus for you, what do you want to know about it? Well, the most important thing you want to know is that it tells the truth. In other words, if your proof calculus allows you to deduce A as a so-called theorem from the rules and so on, A had better be a logical consequence of S. And remember, the meaning of this thing is every interpretation that makes everything in S evaluate to true will also make A true. In other words, this thing here with this, this is called the satisfaction symbol, by the way. S satisfies A, or S entails A, I believe I called it. That's a semantic property which is driven by the truth tables and so on. So everything I evaluate comes out to true, that's fine. Whereas the turnstile thing is a syntactic property, that is, my formal calculus of rules tells me this is a theorem. So everything that is said to be a theorem had better be valid. That's soundness. What is the converse of this? It's called completeness, because after all, you can make a sound-proof system very, very easily by saying nothing is a theorem, right? Totally sound, but not very useful. So you want completeness as well. Completeness says if A is entailed by S, and remember that's a semantic truth table property, if A is entailed by S, then I would like A to have an actual proof. So I want A to have a proof from S. You can't always have both, but for the things we will be looking at, so we will always have both soundness and completeness. What is this last one here? Well, there are all kinds of weird and wonderful things you can prove about a proof calculus. So, in fact, you had semantics, so you know what rule induction is, and basically if you have any, and what you are doing in the semantics course, you're looking at these formal deductive systems which had the specific purpose of giving the semantics of a programming language. But more generally, they are, in my vocabulary, they are all just formal systems in which you generate theorems of one sort or another. And as you did in that course, you can prove all kinds of results about what that system of rules is capable of doing. There is one thing here which people like in particular, and I guess it kind of motivates some of the things we'll be doing later. Let's suppose I have a proof of B from some set of formulas of which I'm writing it now as A plus S. So I have some S from formulas S, and there's a further formula A, which I, if you like, add to it. From that, I have a proof of B. Then it turns out, not for every calculus, but for the calculus I just showed you, and for any decent calculus that isn't effing lousy, that I have a proof of A implies B from S. So this is a natural thing to want to be able to prove. And if you had to prove calculus where this wasn't true, you kind of think, well, maybe I'd better get another one. Anyway. So again, this is meta-mathematics, and one of the cool things from your point of view about meta-mathematics is that it's cool to mention to your friends, you know, and actually I feel for you guys because you're Konskis, right? Now you've got some of your friends are, I don't know, they're philosophy students, they're studying Wittgenstein and all this stuff, and you know, you're learning about Unix tools and they look down on you. So what you should do, there's this book here called Principia Mathematica by Whitehead and Russell, and it's unfortunate. I used to recommend that you buy a copy. It used to be quite cheap. It's not cheap anymore, which is a shame. But maybe you'll pick up a copy of this somewhere, and then you just sit in the college bar reading it, and someone will say, right, that looks cool. What are you reading? And you just hand it over, you see, then they'll respect you. So, what was all that? And actually, I have a page. This is actually maybe the best page is like around page 300, where he proves that 1 + 1 = 2. I'm not joking. This is literally true. So this is logic as it was written around 1910. So like these horseshoes were how they used to write implies. The twiddly thing means negation. The V is or like we use today. And the dots, all those dots are there because for some reason they didn't believe in parentheses. And so there is some weird way that I can't exactly remember in which the dots tell you how the things are bracketed up. So as I said, this will inspire your friends a lot. Okay, now what I want to do, this sort of system we saw here, by the way, in general, is called a Hilbert system. Of course, Hilbert was a great mathematician from the early 20th century, and you have a Hilbert system whenever you have a bunch of axioms and axiom schemes like these, and maybe only a couple of inference rules. This sort of system is often very easy to reason about in terms of meta-mathematics. They're quite simple because, in particular, you've only got one inference rule because the inference rules complicate the meta-mathematics. You've got a few axiom schemes, so it's all very compact. You don't waste your time with the other connectives because they're not very interesting from the point of view of meta-mathematics. And you can prove all those things like soundness and completeness and the deduction theorem relatively easily. But if you wanted to say, let's say you're a computer scientist and you want to implement your logic on your computer, it's basically impossible. A thing that has proofs of exponential length for trivial things is not possible to use. And this reminds me of a joke. So when I was at Caltech, and I don't remember the whole joke, so I'm really sorry here, but maybe you even heard it. There was a thing about distinguishing between people like engineers and physicists and mathematicians by how they would respond if they discovered their bed was on fire. So in every case, they wake up in the night, their bed is on fire, and they have a jug of water next to them. What do? So as I say, I don't remember the whole of the joke, but the mathematician, he wakes up, he sees the fire, he sees the jug of water, he says, there exists a solution. And then he goes back to sleep. So you see, and this is a problem with the proof systems. See, mathematicians, they will talk about a thing, but they never actually do the thing. And that's why they almost never have any children. So here, we're going to do the thing, not that thing, but we want to actually prove theorems in our formal calculus. Now, you saw something like this in discrete maths, so-called natural deduction. I'm not actually going to use these in this course. I'm just showing them briefly in case you saw. I think you saw them with boxes instead. So Gensen defined these things, and the idea is we're trying to make things that look more like the way people prove actual theorems. So like, if I want to prove something of the form A implies B, the natural way you prove it is say, well, let's assume A is true, reason from that assumption, deducing B, and you say, okay, from A I was able to deduce B, therefore A implies B. This means in particular, if you want to prove A implies A, it's like immediate because from A follows trivially, therefore A implies A, right? With a Gensen natural deduction system, instead of trying to find a minimum set of axioms that expresses everything in the logic, you say, okay, we're not interested in minimizing anything. We're trying to be natural. So in particular, for every logical connective, we're going to define them independently of the others and think, like, what is the meaning of this thing? So A and B. So Gensen said, well, there's two things we do with a logical symbol. Either we introduce it, is the word he used, introduce meaning I infer that A and B is true. And how do I infer this fact? Well, I need to know A is a theorem and B is a theorem. Knowing both of those, A and B is a theorem. And he calls that introducing A and B. What else can you do with this logical symbol? Well, he called it elimination. Nothing to do with organized crime here. It is simply, if I know A and B, how can I use that fact? Well, I could obtain A from it, or I could obtain B from it. And the nice thing about this is that as opposed to the Hilbert system where everything comes out in a crazy way, I mean, imagine using that system where and would be defined as some combination of implies and ors, and you have all those crazy axiom schemes. You would struggle to do any of these things. Now, there's a thing I don't like about natural deduction, and the thing is simply this. It is sort of designed the way you would work things out on paper, where these assumptions are temporary. So I am proving here A or B implies B or A. So I begin by assuming A or B. I do a bunch of stuff. I'm not going to explain this in detail because this is not the main system we're using in the course. I'm just showing you this is what it looks like. And the problem is, once you're done with it, you throw it away. And how do you throw it away? Well, you exit out like that. And I'm thinking, when I was designing this course, am I going to mark exam scripts where all the students have crossed out half of their work? There's no way I'm going to do that. And also, it's not very nice for you either if you you did your work and you want to hand it in and like, I've crossed everything out. That's not so good. Now, the big advantage of natural deduction is all the rules look really nice. So, or, if I know A or B, right? That's simple enough. Or we have our friend modus ponens here. It all looks beautiful. So I'm not quite going to do this. Almost, but not quite. But let's have a break first. Maybe that explains why I've never been asked to sign any code of conduct. Right. So we're not quite going to use natural deduction. We're going to use the sequent calculus. Now, the sequent calculus And I don't think you've had this before. As I said, I'm pretty sure you saw something very close to natural deduction last year in discrete math. You've not had the sequent calculus, but the idea is really the same, that we're looking at each logical symbol individually, and we're working with assumptions. So this sequent is the idea that I'm assuming these guys, and in fact I can actually have multiple conclusions where it's enough to prove any one of them. And maybe Genson's real advance was noticing that when mathematicians are actually working on a proof, you make temporary assumptions all the time. So if you like, you have a floating background of assumptions that you make and discard as you. It's a bit like, if you like, nested scopes in a computer program. In a computer program, as you write your code, you create scopes, you introduce variables, you use them, and then you exit the scope, and so on. So he noticed this, and this is the key thing that underlies the calculuses that he invented. The difference is that instead of crossing things out, we are maintaining a full list of all the assumptions alive at a particular point. So it's much clearer what you're doing, although you do have to write more. So we work with things called sequents. That's funny. The German word sequents, I think, or sequents, simply means sequence. But the translator, the guy who first translated his paper, invented a word in English. If he hadn't, this would simply be called the sequence calculus. But, he invented a word, so we have it. Now, this thing is not a formula. You'll note this is a new arrow. We see a lot of arrows in logic because we always want things to lead to other things, but they're always slightly different. So this is not a formula. This is not implies. This is the thing that separates the left side from the right side. But the kind of intuitive meaning is very much like implies. So this is exactly what it means. So what the sequence means, if all the A's, all the left side formulas are true, then at least one of the B formulas is true. And what we do with what we will have a bunch of rules that manipulate these sequents and allow us to prove theorems automatically, really. I mean, the thing is, if you do it, you'll probably find it pretty boring and you'll waste a lot of pencils and so on. But the great thing is, the computer can do it, which after all is what we're all about, right? So the A's, the left side formulas, are being assumed to be true. The right side formulas are goals, or actually you might find it another way of looking at it. The A's are assumed to be true. You could say the B's are assumed to be false, is another way of looking at it. With that way of looking at it, you're actually trying to prove contradictions. That is just a matter of your mind if you want to look at it that way. Now, here's a rather ugly thing. So when I write, I always hated Greek letters when I was a student. I'm very sorry to use Greek letters here, but you do run out of letters. We are using gammas and deltas when I'm too lazy to keep writing long strings of formulas with dots in them just to save space. But there's nothing magic here. So this gamma is just a list of formulas. And now you can get all tangled up in knots as to whether you mean that sequence of formulas to be a list or maybe a list where the order doesn't matter, or a set. Now, I personally prefer to regard them as sets, but this is a personal choice. So things get slightly different. So if they are lists, then you actually need rules that allow you to reorder the elements of a list and all that kind of thing, which I certainly never wanted to bother with. So you're going to see now, when I write just a comma here, remember that these Greek letters, the gamma and delta, are themselves just abbreviating more formulas with commas between them. So this is just another comma. So when I write A comma gamma, I just mean on the left side you've got an A somewhere. Equally, A comma delta, on the right side there's an A somewhere in that list of formulas. And Note that if I have a sequent in which A occurs on the left side and also on the right side, then it's trivially true, right? Because I'm assuming A, and A is a thing that I'm trying to show. So that's trivially true, and if you like, these are the axioms of our calculus. And now I need to give you a few more rules. There will be a lot of rules, and then in the last lecture we will have only 3 left. And why am I so difficult with you? So this rule here, called cut, may be the weirdest of them all, and especially it may be annoying because we will never use this in proofs, never ever. In fact, Genson's great achievement in his work was a thing called the cut elimination theorem, in which he proved, now this is metamathematics, he proved that anything that could be proved with the help of this cut rule right here could also be proved without it, although at the cost of the blow-up is not even exponential. It's this kind of blow-up that you can't even describe using elementary mathematics. So cut allows you to simplify things. It allows you to make shorter proofs. What's going on here, I mean, it's kind of abstract, but I hope I can make it intelligible. And it's often best to view any of this sequent calculus stuff backwards from the point of view of the thing I want to show is at the bottom. How do I show it? So I want to show some sequent here which has the form gamma arrow delta, which remember means I'm assuming gamma to be true. I want to show one of the deltas to be true. How could I go about doing that? And the idea of this rule is one thing you could do, let's suppose there's some formula A, let's call it, a lemma, like a lemma in mathematics. Let's suppose I can prove some formula A. So A follows from gamma, and maybe you can forget about delta for the moment. A follows from gamma, so A is kind of true. So now let's just make A one of our assumptions here and prove delta with the help of A. And that's not really cheating because I know that A is true because I proved it over here. And maybe you can get the idea this is like a subroutine or something in a program where, of course, you could eliminate all the routines from your code and just have a gigantic inline thing, but your program would be very much bigger. Of course, that doesn't work if you have recursion. We don't have recursion here, so it's okay. So why did I show you this rule? I suppose it's always regarded as part of the sequent calculus, although, as I said, we will never actually use it. And the interesting thing here is no logical symbols are mentioned at all. So this is merely about doing things with the sequence and this new formula. Indeed, the reason you never use cut in a computer to do proofs is because the computer would have to think up this formula A, and that would require intelligence. Now, given that using this rule you can find much, much shorter proofs, I suppose it's imaginable that some very smart person will figure out a way, using machine learning or God knows what, to invent suitable formulas and then to find proofs much more quickly than we can do at the moment. But as far as I know, nobody at all is doing that. Right, now I think I should start going through the logical symbols, and this gets kind of tedious, but I hope I can make something make sense here. So, what about not? Not is the simplest logical symbol. And as I said, with the sequent calculus, it generally makes sense to think backwards, to think, I am trying to show not A. How do you show not A? Well, the typical thing you do is you assume A to be true and get a contradiction. Therefore, A must be false. Now, what the sequent rule here is saying is somewhat different. So you're trying to show not A. If you like, the gamma and the delta can be seen as a kind of context for, in fact, you had context in your semantics course, didn't you? So they're very much a similar attitude here that you've got stuff which is around you, which is more or less fixed, and you've got one thing that's changing. So you have, you can call it a context where all the gammas are true. And again, you may be kind of natural to think all the deltas are false. And the thing I'm interested here is showing not A. And if I apply this rule, it says to prove not A, move it to the left side. And then if you can prove the sequent above the line here with A having been assumed to be true, then you have, by means of this rule, proved not A. Now, if you found that song and dance a bit exhausting, you can think of a trivial justification of this rule. If you remember what a sequent actually means, it means if all of those are true, then at least one of these is true. And now if you apply the same logic to these, so if all of those are true, then at least one of these is true. You'll see it works out to be the same here. Okay, now if I go through every one of these, we will never finish, but I think I will at least go through some of them. What about not A on the left? This means we are assuming A to be false, right? Because it's on the left side, I have not A assumed to be true, therefore A is assumed to be false. In order to continue the proof where we are assuming A to be false, we can actually move it to the other side, to the right-hand side, and continue. If we can prove the thing above the line, then by this rule we've proved the thing below the line. Now, as I said, these go on and on, but let me do a couple more. Maybe I should have started with and on the right, because we saw it already for natural deduction. It's the same idea. To show A and B, you show A. In addition, you show B. If you've shown both of them, you've shown A and B. And of course, these contexts, that is, the gammas and the deltas, the other formulas out there, are unaffected here. What about and on the left? Here, I'm trying to prove a thing where I am allowed to assume A and B. Clearly, if I'm allowed to assume A and B, then the two parts of it, namely A and B, should be available, right? And once again, if you don't like my, if you like, intuitive explanation of these, all you have to do is go back to the explanation of a sequence with this meaning here, and it comes out pretty quickly. Now, they go on, and I don't think I want to go through all of them too much, but you might see some patterns here. So, for example, or. Here's, by the way, where the multiple formulas on the right come from. So I'm trying to show A or B. Remember, with the formulas on the right, you only need to show one of them. So it's enough to show A. It's also enough to show B. And you might note this looks exactly like the and on the left rule, except that the and on the left rule has things that the left and right flipped around. And that is exactly how it works everywhere, as we'll finally see in Lecture 12. As for this or on the left rule, this is a bit like reasoning. So if I have two possibilities here, either A is true or B is true, and I want to do my proof, I say, well, there's two possibilities. Either A is true, in which case you prove it, or maybe B is true. You consider that case, you prove it. If you've handled both cases, then you've handled the A case and the B case, and so we can deal with A or B. So again, it makes sense intuitively. It also makes sense if you simply plug in the meaning of a sequent. As for implies on the right looks exactly like the implies introduction that we've seen before. I'm trying to show A implies B. So I assume A to be true, and if I can then show that B follows, then I have shown A implies B. And the somewhat weirder looking A implies B on the left, this actually is kind of modus ponens, but it looks totally weird. You have to show A, right? And then if I know that something follows from B, then something follows from A implies B. I'm sorry, that is the weirdest looking of all the rules. So what you might prefer to do in your mind is say, well, A implies B is not A or B, and then you will see that this rule agrees with what the OR and negation rules do. What you can't do, however, if an exam question says prove a certain formula involving implies, if you rewrite it using not A or B, then you have cheated, right? Because if you're doing a sequent calculus proof, you've got to use these rules on the formula you are actually given. Right. Do I have some examples? I'm kind of wishing that I had... Oh, what the hell have they done? They moved this... Every day a surprise in this lecture theater. Well, I'm going to stick with one visualizer because I think I would lose something if I tried to get two going at the moment. I should say again, why do we do everything backwards? Why am I going to hide everything but the bottom line and then work up? And we have a kind of paradox here because all our logic and rules of inference are written out and they say, if this is a theorem, then that is a theorem. The point is, though, no one ever wakes up in the morning saying, I want to just generate a whole bunch of theorems at random by applying inference rules willy-nilly and seeing what comes out. Because nobody ever wants to just look at a random theorem. What they do wake up doing is saying, I want to prove Fermat's last theorem today. So you write down the thing you're trying to prove, and then you try to break it down, simplify it, and find sufficient conditions for it. And to do that, you have to write down the thing you're trying to prove, and then work backwards until you arrive at a proof of it. And the sequent calculus works perfectly in this way. So you start the thing I'm trying to prove, and of course this is completely trivial. A and B implies A. And I could write this on another piece of paper, but there's so little here, there's almost no point. The point is, also with natural deduction, we only operate on one symbol at a time, and it has to be an outermost symbol. And here there's only one outermost symbol, namely implies. It's on the right side, so only one inference rule even needs to be considered. It's implies on the right. And when we do that, bingo, we get this. Now what can we do? We have only one logical symbol. It's and. It's on the left. We do and on the left. Bingo. Again, there were no choices to make here, no backtracking, no nothing. Finally, we note there's an A here and an A there, basic sequent. You can write a line over it to say it's a basic sequent and you're done, and that is, we have proved a theorem in the sequent calculus. I know that many students get tired of writing these things out, and they do get lengthy, and they start doing little tricks which occasionally they go wrong, but never mind. Here is something a little more interesting, because if you remember this formula from before, this was a thing that's not supposed to, well, this is paradox of material implication. It is a weird-looking formula which maybe some people don't think should be true, and in fact this is not true in constructive logic. You can make a constructive sequent calculus. In fact, all you have to do is forbid more than one formula on the right-hand side, and just like that, you've made your sequent calculus constructive. Anyway, forget I said that. It's not on the exam. We start with this formula. Again, we can only work on outermost symbols. The only one is or. It's on the right, so or on the right is the only thing we can do. See, now we have got two formulas on the right-hand side, and for the first time we have a choice, because we have two outermost symbols. Doesn't make any difference. In fact, I think in propositional logic it never makes much of a difference which one you pick. So may as well pick, which one did we pick? We picked the first one. So we did implies on the right using the first occurrence. Let me repeat myself. If you want to save on writing by combining these steps, it is quite easy to go wrong, so be careful. It'll be over soon. At this point, we have only one symbol left, implies. It's on the right, so we know what to do. And bingo, we have a B and a B. It's a basic sequent, so it's a theorem. And so on, more and more and more. I think, given the time, I don't want to go in too much detail. I think the main thing I would like to emphasize once again is that we have very little choice. Here we have some choice because we have two outermost symbols, right? Or on the left and on the right. We can pick either. I prefer when it's possible, sometimes one of them will give you less writing than the other. I think here both of them are going to cause a split. That is to say, they're going to make two copies of something. So here we did and on the right. You could, as an exercise, try proving this with or on the left. You'll still have a lot of writing to do. Oh, and because I wrote similar here, I see similar on exam scripts all the time, whether the other case is similar or not. Here it is similar. Look, I get it. It's tiresome. But these are similar because, if you look at it, it's exactly symmetric. Only you have a B, there you have a C. So we did and on the right. We could have done or on the left. So the effect is we keep this the same, thank God. And now we've got this thing just A or B. The other one would have A or C, of course. Now what do? We have or on the left or on the right. We can do either. I will do or on the right because this will give us less copying to do. You see, all it does is give us a comma there. So that was an easy step. Now we have only one outermost symbol, the or, so we must do or on the left. Nothing else we can try. And you see we get a basic sequent here, and then in a moment, and on the left is the only choice. We get another basic sequent, and that's proved. That's all wonderful. Not everything is provable, and the nice thing here, this is a formula we've seen before. In the sequent calculus, you actually get a counter model, which is great stuff. It means we have a decision procedure. Again, implies on the right is the only thing we can even try. So here we have two possibilities. It doesn't help. This thing is just not a theorem. I will do or on the right because of less writing. Then the only possibility is or on the left. And now we see we have a basic sequent there, but we don't have a basic sequent here because they could all be different. Now, if I remember to say, if you like, we can regard the sequent as saying all the formulas on the right, on the left are true, and all the ones on the right are false. And indeed, this is, if you plug in those values here, you will make the original formula false. So when we attempt the sequent rules and arrive at a dead end, we actually get a counter model in the case of propositional logic. Now, I just want to mention one last thing while we have time. So, a guy at IBM long ago wrote a paper called Toward Mechanical Mathematics, in which he basically used the sequent calculus to get, I think it was a complete theorem prover for first-order logic, so not just for propositional, but for quantifiers as well. He was using, it was an IBM 504 or some hulking great thing with thermionic valves inside that probably had core memory. It was like really advanced. And think that he was able to prove, and actually, like 400 theorems from here, he proved in a matter of seconds, all based on the sequent calculus. So you see, this is a highly algorithmic way of proving theorems. These days, we have the so-called tableau calculi, even today, that are kind of a generalization of this, which are quite powerful. So that's why we learned this, and I should probably let you go now. So thank you.